People are quiet on the house. Yeah. Thank you all for coming today, and especially a huge crowd for the reading day, where there's not supposed to be anybody on campus, but Alessandro is a big draw. So let me introduce our today's speaker. Alessandro Roncone is an assistant professor in computer science here. He's in charge of the HIRO robotics group, which is human interaction
and
robotics. He's also the associate director of our new robotics program on campus, which has a master's and a PhD program. And he's largely in charge of getting students into that, making sure everything is square.
And especially out of that.
Getting into and out of, yes. Out of has turned out to be a bigger problem. Alessandro did his doctorate at IIT, the other IIT, the Italian Institute of Technology. After his PhD, he went to Yale, where he did a postdoc, and then he came to us directly from Yale. Take it away.
Thank you. Thank you, Jim, for the introduction. And again, thank you all for being here. I hope this is going to be exciting. And to my kids, I hope you're not going to fall asleep. Can you hear me well on Zoom? If you can't, just write it on chat and we can figure it out. So today I'm very excited to talk about the work we've been doing in my lab for the past few years, and in particular after reappointment. And before we get started, just a quick scope check in terms of why we're doing all of this. This is going to be just very brief, but one of the reasons why all the people in robotics are doing what we're doing is because we are all very optimistic and ambitious that robotics is going to be able to solve or mitigate some of the biggest, most pressing issues that we are facing today as a society. Some of these domains we work directly in. Some of these domains, I think they're very cool, so I put them in the pictures, but I have no idea what they are about. And most importantly, I think that some of the ideas we are working on in my lab are also very fundamental and can improve more broadly the field at large, and also some of the domains we are not directly affecting. And to give us some context on how I approach these problems, I want to step back and talk a little bit about my academic journey. I like to joke that I was working on humanoids before they were cool, because now everybody is super excited about humanoids. But I started working with this humanoid in particular, the iCub, back in 2006, which is almost 20 years ago. And long story short, for humanoids, same exact big promises, but also same exact big issues. Not much has changed. But again, it's a very exciting domain. I was extremely inspired about the idea of looking at the neurosciences and looking at developmental psychology and trying to implement these concepts in humanoid robots. And this is also what kind of planted the seed or planted a bug in my mind about this concept of truly understanding what it means to have a body and what it means to operate in the space around our body. Then I moved to Yale in 2018, where I worked on human-centered robotics. This is a work that you probably are more familiar with. But in general, in this area, we work on robots that provide cognitive and physical support to humans, robots that are transparent, and robots that are helping augmenting human capability in a variety of domains. And these two threads are what is framing the research we are doing in my lab right now, and what I'm kind of going to center around for the remaining, for the rest of the talk. And of course, this path was not always smooth. I had my fair share of broken robots, my fair share of crazy experiments. Just to be clear, everybody involved in these crazy experiments is alive and well. And Leo over there, fortunately for everybody, will not have a memory of when I tried to bottle feed him with a Baxter robot. But the thing that I would like to highlight is that this is a marathon and not a sprint, and these dreams are very much alive today. And these are some of the things that are motivating my work. And so let's move into what I think is the core unifying thread of my lab. My thesis is that humans should not only be users or at the receiving end of artificial intelligence. They should be seen as models or as a reference for intelligence behavior. This is not something that I'm not the only person to say that, but I believe it is important to frame our work under this lens and perspective. And of course, I want to just make it very clear, I do think of this as a blueprint. I don't think of this as mimicry. We are not trying to copy muscles or the brain or the cortex. We are trying to look at the invariants, the interfaces, the abstractions that make us intelligent. And so a good metaphor is the difference between mimicking the mechanics of flapping wing design versus mimicking the aerodynamic principles of flight. And we all know which one of the two approaches at the end turned into our aerospace industry, right? And I think that the principles here are similar. So what can we infer from this blueprint, for this human blueprint? Again, I like to go back to my experience, and of course I'm very biased, but I believe that we could be looking at this from this dual perspective. On the one hand, there is an embodied blueprint, so all of the great research that the people are doing in neurosciences, in developmental psychology, and how sensory motor experiences are framing and shaping our learning and our brain development. And on the other hand, there is the social blueprint. This is uniquely human and is part of what makes us human, right? And this is more about how can people collaborate, work together, help each other so naturally and so effectively in a large variety of complex tasks. And of course, today, I'm lucky enough to be able to pursue both of these threads in parallel. And most importantly, I'm lucky enough to be able to do that with a fantastic team of PhD students. You can see here, and postdocs, plus an equally as big and great group of master students and undergraduate students that are supporting my research. And I would like to just spend a second to talk about the fact that these students are the students that are trusting me with all of my crazy ideas. Because I wouldn't be here without them, but also most importantly, they are also the people that are every day kind of criticizing me and challenging me when these ideas need a little bit of sharpening. And so I really like this tension. I think it's a strong trait of our culture as a lab and also a big engine for our progress as a research group. Of course, we also do a lot of different things. With many students come many different research threads. And of course, I think they are all extremely exciting and groundbreaking in their own good. But today, I'm going to be focusing on just a few, just a couple, to just give you an idea of why and how these motivations are shaping our present and future research. So this is the plan for the rest of the talk. I'm going to be talking about 2 papers mainly and a couple of papers around them. But these 2 works, I'm going to flip the script and talk about social intelligence first. Then we're going to dive into embodied intelligence. And then we're going to have a brief overview in terms of conclusion and impact. And if all goes well, we are also going to have a live robot demo because I think it's fun to play around with robots. So we'll see how it goes. All right. So this first work was primarily led by Stefan, who just graduated and was co-advised with Katharina. And the core intuition behind this work is that humans are naturally excellent at navigating complex tasks through structured hierarchical thinking. This is something that is very natural to us. There's a lot of research in human factors, in cognitive psychology, in the neurosciences that tell us that we use these abstractions, especially when working with other people, and this leads to reduced cognitive load, leads to improved coordination with other people, which is the scope of this work. And also, there are some hints at using these structures to improve generalization to new tasks. And to just ground these ideas, let me go through a very practical example, which is preparing a big meal like a Thanksgiving dinner. So in this context, there's a lot of complexity. This is a collective effort. There's family, there's friends. You have all these multiple agents. They are all working in the same space. But it's clear to all of us, or anybody that had this experience, that we are also very, very good at navigating this complexity right away. And we do so because we are able to decompose these tasks in simpler tasks that we can manage more easily. We are able to adjust dynamically and switch roles as needed without rigid instructions. So if I decide to plate a specific dish, you are going to be able to change your strategy and work on serving. And this shared hierarchical understanding is what makes incredibly fluent teams and what is still very, very hard for robots right now. So this led us to this research question, which is how can we have robots and agents achieve the same level of fluency in collaboration? So let's look at how to solve this. This is obviously a problem that we have been facing for many decades, and we have been solving in many different ways. So if the domain is fully controllable and it is possible to specify the requirements, we can resort to classic planning, optimization, or scheduling algorithms. There's a lot of industries that are being created behind these very principles. But when things break is when these principles are starting to kind of fall apart. So if the domain is not controllable or observable, if the requirements are hard to specify, you have to start resorting to learning. And again, there's many different forms of learning. You can use POM-DPs, which is not quite learning, learning from demonstration, imitation learning, reinforcement learning. And I would like to dig a little bit deeper into this concept of reinforcement learning, because I think it's going to motivate and ground the work we've been doing very nicely. So let's look at reinforcement learning more specifically. This is the classic reinforcement learning loop. I teach this course. I've been teaching this course this semester. This reinforcement learning loop has an agent that is performing actions in an environment and receiving observations. And the goal of the agent is to maximize the cumulative returns in expectation. So there is an expert that is designing a reward function R and is giving little cookies to the agent every time the agent does something good. This is something we've worked as a field for many decades. We made incredible progress on this, but there is a dirty little secret to this abstraction. Anybody knows what is the dirty little secret that you can see in this slide? Anybody from my course wants to answer this? Anybody? Yeah. The environment is fully observable, but there's another worse secret in this. Yeah. Reward shaping. So the dirty little secret is that specifying this reward function and this idea of just designing a reward function is a massive problem for the field. Expecting that an expert is going to be able to design a reward function for the robot to perform what you want it to do is a broken paradigm. And so this challenge is what pushed us to a more powerful idea, moving away from expert-specified rewards into the idea of optimizing for what the human internally wants. And this is the domain of learning from demonstration, reinforcement learning from human feedback, preference learning, and a lot of other domains. So if you could continue this metaphor, I would like to frame this under the preference learning perspective in particular. And in this area of work, we are trying to optimize for the human reward, for the reward that the human intends for the robot. And so the framework changes in this way. You might be having a specific internal preference for what the robot is doing, and the task for the robot is not only maximize the rewards in expectation given the state and the action state of the environment, but also to maximize these rewards given the hidden preference of the human. And the goal of this paradigm is that at some point you're going to receive some feedback from the human in some form. Could be physical demonstrations, could be explicit feedback. And the robot needs to reason about what does this feedback tell me about the internal preference of the human. And the problem of this, again, a lot of interesting research. We are still working on this, like this very day. This is a very important paradigm for human-robot interaction. But one of the things that kind of breaks in this paradigm is this idea of feedback. Giving feedback is expensive, is extremely costly. And so what we started to think about is what can we do without the notion of feedback? And in the context of human-robot teams that are working cooperatively on the same tasks, so you don't have a human that controls the robot, but you have them working together as a peer, the idea here is that the human, is also performing a task on the environment. So the question, the first idea here becomes, can we use the actions from the human to infer and to retrieve information about the internal preference of the human on what the robot should be doing. And again, this is a very simple. The key insight here is that if I am working on cutting onions, the robot should be deciding what is the best next task that it should be doing as a consequence of it. So if I'm working on cutting onions, you should probably prepare a pot or something like this. And I can do so because I can observe the human and I can reason about what the human is doing in this context. And lastly, there's another very important simplification in this context, which is the fact that we are trying to work with robots as a team. So I don't want to necessarily control what the robot does. And so the thing where this paradigm breaks is that the humans might not necessarily want to control the robots directly. I have no opinion about what it is you are doing. I just want you to do it, right? And this is something that we expect from other people and something that we want to expect from robots as well. So if that is true, and if we are trying to use human behaviors in order to infer specific behaviors, the problem here is that there's also a lot of information that is missing. This piece of information is not enough. And so what we decided to do was to this brings us to the next idea, which is the concept of creating shared task structures that the human and the robot share and trying to utilize them for streamlining the interface. The idea that they are working together on a task, we can decompose this task with a shared task understanding, and this helps the team work better. And what this allows us to do is to fundamentally clean up the interaction model. We can get rid of the explicit feedback, so the human is not bothered with what the robot is doing, and we can focus only on what we can do as a robot and what implicit information we can retrieve from the environment and what the human is doing. And note that we are looking at this from a purely scientific perspective. It's not that we are going to forget that there is explicit feedback or verbal communication between a human and a robot, is that what we are looking at in this paper is what can we do without this information. And this is our idea of implicit coordination. We want to have robots and agents that perform tasks in complex environments without necessarily burdening the human side. So we did that for this specific line of work with an algorithm that we call H-square, hierarchical ad hoc agents. And the idea here is that we have a hierarchical deparallel algorithm that allows us to decouple goal setting, which is I want to collaborate with humans, with goal achievement, which is I want to learn how to perform specific subtasks to solve Thanksgiving. And the idea is that these representations are going to mirror how the humans approach the collaboration, and this is gonna streamline the interaction, make the team better, the humans happier, and so on and so forth. There's a lot of other little nuggets that I think are pretty interesting from an algorithmic perspective, but the main idea here is that we are focusing on the capability. And the way in which we do it is that we have a two-layer architecture. We have a manager that sets the goals at a lower temporal resolution because it's looking at a longer time scale of solving Thanksgiving. And these goals are communicated below to the worker without necessarily specifying how these tasks should be achieved. The worker operates at a higher temporal resolution because he needs to solve specific tasks like plating. And this temporal resolution is conditioned on the goal that is receiving from the manager. So in essence, what the manager is doing is trying to solve the problem of collaboration, whereas what the worker is doing is trying to solve and understand and learn how to complete the specific subtasks. We do this in this game environment, which is called Overcooked. This is inspired by a real video game that a lot of people play with, including Stefan, that was working on this. And the idea is that I call it collaborative competitive games. The idea is that there are two chefs, a human and an agent, and they are cooperatively cooking soups. The faster they get, the more score, the better the score. And I really like this environment for a number of reasons. First off, there's a lot of baselines. A lot of people have worked in this space. There's hundreds of papers being built on this interface, which means that there's a lot of great works we can compare against. The second one is that differently from typical human-robot interaction, where the human is so much more capable than a robot, the capability of the human and the agent are comparable. So we can truly inspect these ideas of coordination, and especially real-time coordination in a competitive setting. There's also a lot of different environments that test different forms of coordination. So it's very hard for a classic agent to be able to perform well in all of these environments. We ran a relatively large set of user studies. This is also, our work was also in collaboration with Anthony, who ran another set of studies that are including gaze as a measure to anticipate human intent. We also have a couple other papers on this. But from these results, we learned that, first off, from an algorithmic perspective, our agent is better at working with other agents, and both other agents and unseen humans. I would like to highlight here that, again, all these scores don't matter much to anybody, really. But the important thing here is that not only we were better, 20% improvement over the best performing system, but we are also doing that with 15 times fewer time steps. So these systems had 1 billion episodes, and in particular, I think it was FCP or HIPT, billion episodes of training, whereas we could do it with 66 million. And we also ran this user study in which we demonstrated that people were very happy when playing with our agent with respect to the baselines. Our system was perceived as being more fluent, more trusted, more understandable. And all of this is without explicitly modeling the human, which is what some of the other baselines are doing. And this is because people were telling us that one of the reasons why they really liked our agent is because it was consistently task-oriented. It wasn't bothering the person too much. It was not interfering too much with what the person was doing. It was just doing the job, and this is what people were appreciating. Okay, so to conclude, there's a question in chat, or, oh no. Thank you, Bobby. Just said that he can hear me. To conclude this, here are the key takeaways. The core ideas is that if by using these shared task structures plus implicit understanding of what the human wants from their behaviors, we can create agents that are better at aligning with humans in complex state-of-the-art tasks. And this is a very small step, but I think it is a step towards the broader problem of AI alignment, which is a big issue in artificial intelligence right now, which is ensuring that our AI systems are truly working in concert with what we want from them. So I'm very happy that Stefan pursued these lines of work. He graduated, now he's very happy about the house and so on and so forth. But what I'm very excited about is also what this work enables next. And I would like to highlight two things. The first one is what I like to call extrapolative generalization, which is the ability to do zero-shot adapt to distribution shifts and solve these complex tasks without additional training or fine-tuning. We tested this by creating environments that are different than what the agents were used to. And we see that by just changing a little bit these environments, the performance of these state-of-the-art systems dropped significantly, and these agents significantly overfit. So you can see here that this was the performance of the environments that were observed in training, and this is the performance of the same agent with the new environments that were not perceived before. So you can see how this demonstrates that all these agents are significantly overfitting to their training set. Our agent kind of maintains performance. So you can see here from 157 to 127. And the reason is that this structure allows the model to learn more generalizable concepts about both how to perform the task and how to collaborate with people. So this is very exciting. And another one that I'm very excited about is what I call interactive adaptation. This is something that I've been starting to work with Jake, who was then a PhD student at Yale before leaving Yale. So now he's a postdoc, he's over there. But this is the idea of creating systems and agents that are able to modify their behavior at inference time. This is something that none of the baselines have, and in general, this is a very open problem in artificial intelligence. But because we have this hierarchical structure, we can use the structure to conditionally bias specific actions in the manager without necessarily requiring additional training. So if the person has some form of strategic advice that is very hard for the robot to find, like grab both plates if both pots are, grab the plate if both pots are full, we can look at the probability distribution of performing each of these actions. And we can automatically change this distribution to fit with the request. And this generates a behavior that was not possible before and was not explored in training. So again, we tested this with our little game, and we showed that this also leads to further improvements in terms of performance and so on and so forth. But what I'm excited about this, and again, we did work on a similar ideas for this paper that Jake published a couple of years ago, is that it can enable enable systems that are able to be coached and adapted on the fly after you've trained them. So you might be asking, where are all the robots? Because you thought this was a robotics talk. And indeed, I haven't shown a single robot so far. But we did do a lot of robotics work in this space as well. This was primarily led by Ishan and Claire, who are co-advised by Brad. Brad, I hope you remember when and where this picture was taken. And I would like to highlight just three works here. Ishan has been leading this idea of environment design, so creating environments that allow the human and the robot to be more legible and more understandable, so mutually beneficial algorithm. And also recently explored this in the context of preference learning, which was the algorithm that I've been showing before. So the systems that can reason about and use counterfactual reasoning in order to create and query the person about specific decision-making choices that allow the agent to infer internal preferences of the user. And Claire, together with Maria and Brienne, has been working further on this idea that there is a notion of optimality in artificial intelligence, and this notion completely clashes with what we expect from artificial intelligences, which is legibility and understandability. So we are looking at trying to create agents that are able to change their behavior after they have trained for optimality, and sacrificing a little bit of this optimality in order to make the agent more legible and understandable. Okay, so this ends my first part, and it brings me into my second part. Do you have any questions for me before we move on? There's going to be more robots here for sure. Any questions? Yeah. That is a fantastic question that I talk about with my students all the time. In this work, they are manually coded. But again, I was talking to Chihui, I don't know where you are. Yes, a couple of weeks ago, that right now with LLMs, we can literally just make them up on the fly. So this is, again, it's more of a limited, like we haven't focused really on this. We did have works in the past in which agents could learn these structures on the fly as they were building and working with people, but that was not the scope of this work. Also, from a task perspective, this game is pretty simple. Great question. Other questions? Okay, so let's move on. Again, I'm going to talk about one single core work. This is primarily led by Natalia. And if you remember, I said that I had this bug in my mind since 15 years ago. And I'm very excited about this work because I think that this is finally scratching the itch a little bit in terms of trying to look a little bit deeper at these problems. So to understand where we are coming from and where we are going with this, I would like to spend, oh, there's some questions in chat. Sorry, I should have repeated the question. You're right. I'm going to do it next. Thank you for answering. So yes, to understand this approach, I would like to look at the same blueprint that planted the bug in the first place, which is the neurosciences. I personally think they are extremely fascinating, and I've read a lot about the neurosciences, but beyond that, I think there's a lot of inspiration we can take for the future and the present of robotics. And in particular, these two concepts of body schema and peripersonal space. These are two neural constructs that are fundamental for our physical intelligence, but also for our cognitive development and cognitive intelligence. On the one end, there is the body schema, which is the dynamic functional map of our body's capabilities. It is action-oriented, it is functional, and it adapts in real time depending on context. This is an experiment 20 years ago where they were showing that some neurons can expand their representation of the body and include tools dynamically as the monkey is operating this tool. And the other one is the peripersonal space. Peripersonal space is a map of the space around the body. It's very important for us because it's the space where physical interactions are possible. Also, this one is deeply connected to our motor control system, and of course, is deeply connected to our body schema representation. Also, this representation is dynamic and expands and contracts based on the task requirements, based on our body, and based on our configuration and motor intent. And this one in particular is extremely complex and fuses vision, touch, post-perception, and a lot of other sensory feedback we might be getting from our body. And these concepts are at the foundation of our physical intelligence. These concepts is pretty well known right now in these domains, that these are extremely important for our own intelligence. But I believe that there is still a big gap between these ideas and what's possible right now in robotics. Because body and space representations are essentially a bottleneck for modern robotics. They are both a bottleneck and an afterthought. The body, in general, is a static constraint, is modeled geometrically. We can model it mechanically, and there's a lot of ways in which we can model a body, but it's still static and not necessarily something we think about. It's more of something that we use. And the space around us is binary. There's collision, there's free space. Contact is typically failure mode. But the issue there is that manipulation, which is the essence of robot embodied intelligence, is nothing but identifying and controlling contact. So there is a conflict there. And this is true for both classical robotics and robot learning. In classical robotics, there's not necessarily a specific notion of embodiment, but there is a notion of if you train a giant network with enough data, we are going to witness the emergence of something that is going to represent my embodiment. But of course, this is much more direct for classical robotics because we have to use a model in order to perform tasks with our robot. And I would like to also here show a very simple example. This is an example that I'm going to carry throughout this work, this presentation, and this idea of just rotating a ball around its axis through continuous contact. So this is something that we can do very well. I can do it with my wrist, I can do it with the back of my hand, I can do it with my arm, I can do it with my feet, right? And the idea here is that we are not creating special control actions in order to perform these tasks. We are abstracting away from our embodiment. We are performing the task irrespective of the part of the body that is performing it. And this is still extremely hard for robots right now. So actually, interestingly, we looked at this because we were interested in understanding touch and contact. And so we looked at the state-of-the-art algorithm for this, which is IDTO. You can model this from a trajectory optimization perspective. IDTO is great. It does the job. You can see here that you can twist this ball. It's a very complex algorithm. But as we were kind of delving deeper into this, or actually as Natalia was delving deeper into this, we also realized that there's a lot of failure modes that this algorithm doesn't model. For example, this is not a physically possible motion because the ball will go through the body of the robot, or there were convergence issues over there. And so if we're looking at actually the performance of this algorithm in this specific task, we are having very, very high error rates. And so we sat down and we decided, hey, let's work on improving this algorithm. Natalia spent many months in trying to improve this algorithm, and then we realized that this is not an algorithmic problem. This is a problem of body representations. The reason why this algorithm doesn't work well, this algorithm does a lot of cool things, but the reason why this algorithm doesn't work well, and sorry if these videos are not great, is because the physical representation that this algorithm is using is pretty basic. And so we are limited not by the algorithmic choices, but by the tools we are using to demonstrate these algorithms. And so our idea then became, can we change the body representation without necessarily changing the algorithm? And can we show that this is going to improve state-of-the-art algorithms, state-of-the-art techniques? And this should work across motion planning, control, optimization, and ideally learning. We demonstrated the first three, still working on the third and the fourth one, but that's where we are going towards. And again, to see how it's done today, we can look at this from this spectrum. This is something that we've been using, kinematic models is something that we've been using for the past 40 years. It's very fast. It's a very bare-bone geometric approximation of a robot embodiment. I teach it in my undergrad class, right? Everybody uses it. It's very simplistic, but it does the job. On the other hand, we have high-fidelity meshes. You can get them from a CAD of the specific robot. They are also not usable in practice because they are extremely complicated, computationally expensive. They are not differentiable, so you cannot use them for robot learning, for example. But what's emerging more and more in this space is what happens in the middle, which is this idea of spherical approximations, where a robot's body is approximated by a set of spheres connected together to fill the volume, to fill the body of the robot. This is pretty nice because they are faster, they are higher fidelity. You can do very fast collision checking because it's in constant complexity. It is also analytically differentiable and parallelizable, which is very good. But the problem is that these techniques are typically revolving around a manual process when there is somebody that creates these spheres for the robot and never touches them. And this is a problem because we would like to have these rich dynamic body representations that we can use in many different ways. So we looked around and we also found that there is an entire field in computer graphics that is dealing with actually creating automatic spherical representations that are improving fidelity and physics for video games and so on and so forth. The problem with these techniques is that they are not directly applicable to robotics because they don't care about what we care about. And so what we did was to bridge the gap between what's possible right now in computer graphics and what people have been doing in robotics. And the way in which we do it is through this very elegant, in my opinion, optimization algorithm. The task here is that you're given a mesh, so a 3D representation of a robot or a specific link or a specific object, and the goal is to fill it up with spheres whose number you are specifying a priori. This algorithm is a very nuanced algorithm that covers a number of different losses, so we can tweak and twist and change all of these parameters to have different embodiments or different representations that serve different purposes. We are also doing some steps of dynamic adjustment as we are performing this optimization. Here you can see that some of these spheres are being removed, some of these spheres are being added, but the end result is that you're going to have a final packing that is optimized for this specific mesh, and most importantly, is fully compatible with any and all the frameworks that we are using in robotics nowadays. So this is a universal robot description format. Everybody uses it. And so by being compatible with it, we are making this technique readily available to any roboticist out there. So let's look at how it works. Please pay attention to the top left. 1, 2, 3. Done. Very fast, which is very good. But here you can also look at it and slow it down a little bit. You can see here how, again, we fix the number of spheres, and then this optimizer moves their centers and their radii around in order to squeeze into the structure. You can see also some, you can see also some spheres being added, some spheres being removed. And at the end of this very fast process, you have a 3D representation that is not a mesh, it is much simpler, and that we can use for a lot of cool things. As I said, there's a lot of losses in our optimization. We can do a lot of interesting things. We can have different resolutions. So, for example, 3 spheres per link if you want to have fast motions, 50 spheres per link if you want to be high fidelity and you want to do something that is extremely hard and complex. You can do it for different robots. This is the spotter robot that Chris's lab uses. This is the humanoid that Nicolas's lab uses. And as a matter of fact, Nicolas' students are already using this technique for their own control algorithms. Most importantly, we can tune these parameters and have different versions of Morphit that suit different purposes. So here we have 3. We have Morphit V, which is maximizing for volume coverage, and also is the one that is the most compatible with our baselines from computer graphics. We have Morphit S that maximizes for surface coverage. And then B means best or balanced, which means a little bit of both. We show that we are better than the state-of-the-art at physical fidelity, especially if we are reducing the number of spheres. We are also 2 orders of magnitude faster than the baselines are computing this, which is very good because, again, in computer graphics, they don't care about these algorithms being fast. We do care about it because we have to work real time with the robots, right? And we also ran another set of evaluations. We are showing that our systems are better at collision detection. This is a simulation showing a robot in this complex environment with hundreds of obstacles. And we are showing that our system, and in particular Morphit B, is the best at detecting collisions in this space. We ran extensive testing for contact-rich interaction. So we are getting towards what was saying before. Here again, we show that we can interact through contact with this ball with different body parts, and we also show that our system, the one that maximizes for surface coverage, is the best at performing this task. Maximizing for surface coverage means that we have a very precise matching between the surface of the robot and the spherical representation. And we also operate, kind of plug this in a standard motion planning architecture, and we test it across a large variety of environments for manipulation in clutter. You can see some of them here. And we again show that our dynamic and flexible representation can allow for higher success rates across a large variety of tasks. And lastly, if you go back to the problem of whole body contact planning, we are also showing that this was what I was showing before, just by plugging in this representation to the algorithm, so we haven't touched the algorithm in any way, we are going to be able to significantly improve the performance of this algorithm in this context. So here you can see that the robot can interact with the sphere with many different parts of their body without incurring in convergence failures or invalid configurations. And we can also see from this graph that just adding Morphit significantly improves and reduces the error rates of this state-of-the-art algorithm. Again, just to wrap this up, the main idea and the reason why I'm very excited about this work is that this is not only an algorithm to create flexible body representations that is available to the broader community and readily, you can plug it into your software right away. But this is also a good example of this idea that we should be looking a little bit deeper at this concept of body representations. Just by understanding better what it means to have a body and what to do with it, we are going to significantly advance, or at least that's my hope, the state-of-the-art in the field. I'm also here very excited about the future work that comes from this method. And in particular, as I mentioned, we would like to work a little bit more explicitly within the framework of robot learning. this representation is differentiable, which means that it is compatible with the most important tool that people are using in this space, which is gradient descent. We can blend this representation in with these more recent tools, and I believe they're gonna lead to significant advancements in capability. I'm most excited about the fact that this is computationally efficient, so we can have compact physics simulation for world models for systems that can reason around complex tasks and imagine how to perform complex tasks in their environments. So this ends this part of the presentation, but this is also a nice segue into a couple of works I want to show today. How are we doing with time? Nice. And in particular, this idea of robot learning. This is a work that Anuj has recently published at Corl. Anuj is not here today because he's still flying back, but this is a glimpse or an example of how we are using robot learning and how we're grounding robot learning with physics. So here we are using a diffusion-based architecture. And in particular, we are looking at the problem of integrating this diffusion-based architecture with dynamic constraints. State of the art in foundation models in this space is primarily centered around kinematics constraint. So you can see a lot of cool things, but yes, primarily geometry-based motions, whereas these systems are still struggling when incorporating things like forces and torques and torques of the motors and complex interactions with a large variety of objects. And in this specific work, what we focused on is this issue of having a robot, we call it supernominal payload manipulation, having a robot like the Franca, which is rated for 3 kilograms, and asking the robot to move a 6-kilogram payload. If you do it with normal classic approaches, you are going to have a robot going into fault. The robot is going to start the motion, and then some torque is going to be exceeded as some motor. Typically, in this configuration, is going to be one of these motors because are the ones that are going to be most trained by this motion, and the robot is going to stop. But we know very well that if we incorporate this notion of dynamics, we are going to be able to do different types of motions that allow us to stay within the bounds of operation of this specific platform. And that's what we did here. So I'm going to skip a little bit because I think that the cool thing is just showing the videos. So here is the robot. Again, this is a 3-kilogram robot. Here's the robot that is performing tasks and actions on a 7.2-kilogram payload, which is 2.4 times what the robot is allowed to do. And again, what this diffusion model is learning is to perform different actions depending on the payload. We are conditioning the learning on the payload so that the robot, when the robot knows what the payload is, going to perform these different motions depending on it. We tested it with a lot of different things, watermelons, laundry detergents, and it works really robustly. And my intuition here is that we are training this with classic methods, so motion planning and control methods, which have high failure rates when you're going into this area. But this system is learning to squeeze as much information from these failures in order to then perform better and more robustly than classic approaches. Also, shameless plug that Anuj, together with Claire, have been working on converting these ideas into a startup, which we called Boulder Born. I really like it. And we are finalists for the Lab Venture Challenge, which is like seed grants from the venture partners. We are pitching October 22nd. So if you have time, you should come. The Art Center is open to the public and free tickets, and you should come and cheer. I'm just waiting because you're taking a picture, but which means I'm going to see you there. Okay, so last work I want to talk about today, which is the demo. So Carson and Caleb, which are over there, have been working for the past few years on robot skins, which is what you can see here. We have a fully automated pipeline that from any robot, again, you can automatically generate a set of skins that we can then 3D print with a multi-material 3D printer. And in a single print, we can have capacitive sensing capabilities that we can then deploy in any robot. This was a paper we published for ICRA. For this ICRA, still under review, Caleb and Carlson have worked on taking the same approach of using this procedural generation pipeline and embedding further capability into this technology. So in particular, trying to understand how can we use capacitive sensing for not only detecting contact, but also detecting proximity. And this is something I'm very excited about because it goes and leans into this idea of perceiving the space around the body and creating this sort of an aura around the body that the robot can operate in. And again, when my talk is going to be finished, you should, is it working? When the robot, when my talk is going to be finished, you should come and play around with this. This is also 3D printing, which means the design space is endless. We can have different sensors. Here we're using some time-of-flight proximity sensors, but we can also use the technology that Carson has developed to perform these complex tasks in this space. I really like this idea of being able to negotiate spaces with robots and the robots being intuitively receptive to this concept. That's what we would be doing if we were to operate with a person. And that's what, in my opinion, these technologies are enabling. Again, later we're going to have all the sensor data on the big screen, and I hope it's going to be a little bit more interesting. But this is just, again, an overview of how we are trying to tackle this project, and also, of course, super hard. Understanding we had to use a relatively complex algorithm to understand the wiring that goes through this. All this is automated, but most importantly, detecting objects in proximity with capacitive sensing also goes through machine learning. We cannot do this from a modeling perspective because of the complexity of capacitive sensing. And especially multi-touch and so on and so forth. But again, hopefully later you're gonna see this with some nice visualization is gonna be a little bit better. Okay, so this ends my second part. And before I move on to the conclusion, any questions? Okay, so let's talk about it. Yeah. Normal kinematics is differentiable in itself, but we can't have a differentiable representation. So I can have a fixed kinematics. I can have trajectory optimization to minimize, to do reaching and so on and so forth, which we do all the time. But I can't change the kinematics in a differentiable way, which is this idea of having flexible bodies, flexible body representation. Right? That's a fantastic question. And I should have probably said it more explicitly. Okay. So let's go back. Let's go to this final high-level conclusion. I hope I'm going to convince you that this is cool beyond the works I described. And I want to mention this concept called the bidder lesson, which is a very famous concept in artificial intelligence. It comes from a blog post from Richard Sutton. And it's this idea that general methods that leverage data and scale will always outperform handcrafted solutions. And this is what led to incredible things, including ChatGPT and Claude and all these other things, but also including these incredible videos you can see here from top companies that spent a lot of money, but also are able to show these impressive capabilities. And this comes from this very idea. But on the other hand, again, these systems are excellent at general task reasoning, as visual understanding, language understanding, some degree of generalization as well. But on the other side of the spectrum, there is this counterpoint, which is what Rodney Brooks calls the better lesson. So after Sutton came out with this blog post, a couple of weeks later, Rodney Brooks had his own interpretation and version of it. And again, this is my interpretation of what they said, especially in light of the fact that this was 6 years ago. But what they are saying in these blog posts is primarily what I'm saying here. And what the Robotics is saying is that this idea of scale, or this idea of generalization through scale, also leads to shallow generalization, to brittleness, auto-distribution, to weak compositional causal reasoning, and to a lot of other things that are even more important for embodied intelligence. And funnily enough, yesterday I was looking at our lab's OneDrive just to find videos and stuff like that for this presentation. And I found this screenshot that Anuj took of a presentation from Josh Tenenbaum from MIT. I have no idea where this is coming from, but I think that he says it very, very well. The difference between the intelligence being the end result of learning, the end result of scaling up, versus intelligence being the foundation of learning, being what allows us to learn and to grow up. I think it's a fantastic metaphor, and also very applicable to some of the things that these people are saying. So which of the two fronts do you think I'm in? They want to do it, yes. But hopefully, I spent a lot of time thinking about this, but also I want to add a couple of perspectives on this that are going to contribute to this space. My idea is that the embodied intelligence is the result of explicitly weaving together these three concepts of body, space, and action. And I think that this is complementary to, for example, the paradigm of sensing, planning, and acting in robotics. I think that sense, plan, act is very hardware-centered. It's a mechanistic interpretation of what it means to be a robot. I hope and think that this would help transition this field towards more of a computational interpretation of intelligence. And to me, body means a representational prior that simplifies our understanding of the complex sensory-motor stream. And within this context, the idea of space is, yes, a complex multimodal interface where the self meets the world, but this interface is mediated and simplified by and conditioned by the body schema. Because I have a body, my understanding of the space around me is going to be simplified and different than your understanding of what's around you. And again, under these concepts, I would like to interpret action as thinking through the body. I want to abstract away these core concepts that we can apply, and it's a concept that we like to call morphological intelligence. So thinking about the body, conditioning your action by this representational prior, and trying to look at what's possible in this space because of this abstraction. And of course, you are an embodied intelligence that is also socially interacting with other embodied intelligences, for example, people. And so the definition of social intelligence then becomes, how can we weave these concepts with the social fabric of human AI teams and society at large? And this is fundamentally what our research is about. I hope I convinced you that there is merit to this very explicit way of interpreting or at least looking at what we are doing in my lab, or looking at what drives our current and future research. I hope this was an interesting set of videos and presentations. And with that, I thank you, and I'm happy to take any questions. And sorry to the people in chat because I didn't repeat the question. Any questions? Yeah.
Talking about forfeit B, but why do you care about the volume?
So the question was in the morphit algorithm, why do you care about the volume? And this is a fantastic question that I didn't have time to spend, I couldn't spend enough time on. But the main idea here is that you should be using different body representations depending on what it is you're doing. So in the context of collision avoidance, so we are navigating a complex environment, I just want to have a robot that is able to avoid obstacles and not get hurt or not hurt people. I want to have a representation that maximizes for volume coverage. And this is an effect of this you can see here. It's a representation that fully covers my volume and some. right? I'm simplifying from meshes, which means that there's always going to be an error between the volume and the representation. But the idea is that I'm covering the entirety of the volume, right? If I'm doing precise things, I want to do the opposite. I want to stay within the volume because I don't want to be able to control something that doesn't belong to my body. And so we show, I don't think it's these two. I think it's actually, no, it's actually probably those two. We show that there is a, this is one of it. There is a trade-off that we can have. Again, it's a simplification, but in our case, we can successfully navigate and maximize and actually minimize this trade-off for the purposes that we are showing here. Does it make sense? Yeah.
Question. How can we support robots that can dance with humans?
This is a good question. How can we move towards robots that can dance with humans? I do think, and I hope you're going to be convinced by now, that dance is an extremely complicated task. I'm very bad at it, but I'm still better than robots. But the problem of dancing is the problem of bringing all of these things together and doing so in a fluent, natural, transparent way that doesn't burden the person you're dancing with, right? So again, unfortunately, you couldn't see it from maybe I can do it here. I'm going to change my camera, and I'm going to show you on the robot. Is it still working? No, yeah, I was asking about the robot. But dance is an extremely interesting problem, in my opinion, because it is about negotiating spaces. It is about creating a coordination, but it's also about not thinking too much about it. And that's the type of things that I want to achieve with this line of work. Luckily for me, again, I have a lot of students. Sri Krishna is working on similar concepts. So the idea is that we want to understand how can we have robots that are expressive and that can navigate these complexities in a way that is natural to people. And I do think that it's fundamentally speaking to this trifecta of understanding your body, your space, and how to act in your space together with the other person. Great question. Yeah. It is limited to the primitive shape being a sphere. And there is a good reasons for it. First off, a lot of people are using it. And second off, a lot of people smarter than us decided that it's the best representation. I do think there is some merit into looking at ellipsoids because they can better cover specific areas, but we haven't done anything in that regard. But spherical representations have some algorithmic advantages that I think they are kind of just so natural. So that's the first thing we tried. But yes, it is limited to spheres.
Maybe one more.
The kids are not sleeping.
All right, if there's no more. Let's thank Alessandro.
Thank you, everybody.